Hey everyone, today we're diving deep into the digital courier service that's running constantly inside your computer, transaction layer packets, or TLPs for short. These are, without a doubt, the core packets that make everything in PCI Express actually work. We're going to break down exactly how they move your data, requests, and commands across a PCIe link.
To really get why PCI is so amazing, you gotta look at what it replaced. The old system was a parallel bus, and honestly, it was a mess. Imagine a huge, tangled highway with dozens of lanes, everyone trying to shout over each other at the same time. It was a bottleneck nightmare. PCI came along and replaced all that chaos with a super clean, high-speed serial system that uses packets. It brought order to the madness.
So, here's our game plan for today. First, we'll talk about why switching to packets was such a revolution. Then, we'll literally dissect a packet and see what's inside. We'll cover all the different jobs these packets do, track one on its round-trip journey, and wrap up with the really clever features that make the whole system so efficient.
All right, let's jump right in with this massive shift in thinking. Moving from those old shared highways to a private courier system wasn't just a small step. It was a complete revolution in how computers talk to themselves.
So, instead of different components fighting for their turn on a shared set of wires, PCIe does something brilliant. It breaks everything, and I mean everything, down into these perfect little digital parcels. Seriously, think of them like courier packages. Each one has its own address label, its contents, and its own tracking number, sent through a dedicated point-to-point delivery service. And this whole packet approach, it comes with some massive advantages. You get incredibly reliable delivery because there's error checking built right in. It allows for super flexible routing, so a packet can easily find its way from, say, your graphics card, through a switch, all the way to system memory. And the best part? These TLPs carry everything. We're talking data requests, the replies to those requests, and even system messages like interrupts. They're the universal mail carriers of your PC.
Okay, so if these TLPs are digital parcels, let's go ahead and unbox one. What are the key parts that make these things actually work? At its heart, a TLP really has three main sections. First and most important is the header. This is the shipping label. It's got all the critical info. Then you have the data payload. And notice this is optional. This is the actual stuff you're sending, like a chunk of a file from your SSD. And finally, there's another optional part called the end-to-end CRC or ECRC. Think of this as an extra insurance policy, a final error check to make sure the package arrived perfectly intact.
We have to spend an extra second on the header because this is where all the magic is. The header is what gives the TLP its identity. It tells the entire system what kind of package this is, where it's coming from, where it's going, and any special instructions for how to handle it along the way. It's the brains of the operation.
Let's break down that shipping label using our courier analogy. The requester ID? That's the from address. It says which device sent the packet. The address field is the to address, like a very specific location in memory. The tag? This one's critical. It's the unique tracking number. The type tells you the service level. Is this a standard memory delivery or a top priority configuration package? And finally, the attributes are the special handling instructions, like fragile, or in this case, no snoop.
Now, just like your favorite shipping company offers everything from overnight letters to freight shipping, PCIe has different kinds of TLPs, each one designed for a very specific job inside the computer.
You've basically got four main types of requests. Memory requests are the workhorses. They're constantly moving data to and from your RAM. Configuration requests are what your PC uses when it boots up to figure out what's plugged in and how to set it all up. I/O requests are pretty rare these days, mostly just for older legacy devices. And then you have message requests, which are really cool. They actually replace old physical wires for things like interrupts or power management alerts, turning them into digital packets instead.
But remember, this is a two-way street. When a device sends a request, like asking to read some data from memory, it doesn't just fire it off and hope for the best. It's expecting an answer, and that answer comes back in the form of a completion packet. This packet either has the data that was requested, or it provides a status update, like delivery successful or address not found.
So, let's put this all together. Let's follow one of the most common transactions from beginning to end, a simple memory read request. Let's track the package.
Here's how it plays out. Let's say your network card needs to grab some data from system memory. First, it builds a TLP. It sets the type to memory read, plugs in the exact memory address it needs, and gives it a unique tag, a tracking number. Then, it sends that packet out. The system's switches act like postal sorting centers, routing that packet to its final destination, the memory controller. Once the memory controller gets the data, it packages it up into a completion TLP to send back. And here is the absolutely brilliant part. It uses the original requester ID to know where to send the package back to. But how does the network card know which specific request this data is for if it sent out 100 requests? Well, the completion packet includes the exact same tag, the same tracking number as the original request. That's how everything stays perfectly in sync.
And there you have it, the full round trip. Request sent, data received. But the real genius here is that the PCI link doesn't just sit around and wait for the reply. It can send tons of other packets while it's waiting. That's called a split transaction protocol, and it's a huge reason why PCI is so incredibly efficient.
All right, for our last section, let's look at some of the special handling features that make TLPs not just effective, but really, really smart. This is the stuff that pushes performance to the next level.
So here's a practical question. Data doesn't always come in nice, neat packages, right? What happens if you only need to change a few bytes at a specific address? Are you forced to send a mostly empty packet and just waste all that bandwidth?
Nope. The answer is something called byte enables. These are special fields in the TLP header that act like a little map. They tell the receiving end exactly which specific bytes in the payload are the ones it should pay attention to. This lets you do super precise, partial transfers without wasting a single bit of bandwidth. It's incredibly efficient.
And TLPs can carry other performance tuning tricks too. The no snoop attribute is like putting a do not disturb sign on the CPU's door, telling the system it doesn't need to waste time checking the CPU caches for this data. Relaxed ordering lets faster, unrelated packets jump ahead of slower ones, preventing traffic jams. And traffic class is all about quality of service. It lets the system prioritize really important packets, like for a video call, over less urgent background tasks.
So, when you boil it all down, what's the big takeaway? Transaction layer packets aren't just simple boxes for data. They are these sophisticated, incredibly reliable, and absolutely tireless digital couriers that form the foundation of all high-speed communication inside every single modern computer.
And that leaves us with one last thing to think about. We've seen how these packets evolved to handle the needs of today's systems, but as our appetite for data, for speed, for AI continues to explode, what new features and new capabilities will the next generation of these digital couriers need to deliver?